When plotting a new canal, gravity is the only engine. The ideal route traces the watershed, the continuous ridgeline dividing two valleys. By staying at the highest local elevation, a canal avoids crossing any of the natural rivers or streams draining into the valleys below. But geography rarely cooperates for long. Eventually, the terrain forces the canal to descend. When it does, its artificial path will inevitably intersect with the perpendicular flow of natural drainage. Allowing these two distinct water bodies to physically mix creates immediate operational hazards. Unpredictable storm runoff would flood the controlled canal system, disrupting supply consistency and risking breaches in the canal banks. This unavoidable intersection makes cross-drainage works a requirement. Engineered structures designed to physically isolate the two flows so they can pass one another without interruption. At every intersection, the designer faces a choice. What type of structural enclosure will best facilitate the crossing? This selection is never arbitrary. It is governed entirely by evaluating the vertical relationship between the canal and the natural drain. This diagram shows the four critical metrics used in this comparison: the physical bed levels of both channels, the canal's full supply level, or FSL, and the drain's high flood level, known as the HFL. The core operational rule is a strict mathematical check. Engineers always compare the lowest physical point of the structure on top against the maximum water level of the structure on the bottom. Memorizing structural names is insufficient for field design. You must apply this exact mathematical hierarchy to determine the correct solution for a specific site. Let us examine the first primary orientation. The artificial canal physically passes over the natural drain. This schematic illustrates the first condition. Notice the canal bed is situated well above the drain's high flood level. This gap is the clear head. Because the natural stream has open air above its maximum flood line, gravity alone governs flow. We call this an aqueduct. Now look at what happens when topography pushes the drain's HFL upward until it is higher than the canal bed level. The natural drain water is now physically constricted by the underside of the concrete canal trough. This intersection defines a siphon aqueduct. The immediate loss of the open clear head completely converts a simple, gentle, gravity-fed drain into a highly pressurized siphon system. The system inverts when the natural drain physically passes over the artificial canal. Here, we evaluate the drain bed against the canal's full supply level. The drain bed rests well above the canal's waterline. With a clear head maintained for the canal below, we have a superpassage, functioning identically to an aqueduct, just reversed. If the canal's full supply level rises higher than the drain bed, the orientation changes again. The canal must now operate under siphon action to pass underneath the physical bed of the drain. This structure is a canal siphon. Prioritizing the undisturbed flow of whichever body is on top dictates the pressurized structural enclosure for the body on the bottom. Moving from theoretical cross-sections to the actual application of raw field survey data allows us to verify this matrix. Consider our first field case. We have a canal bed level of 120 meters and a drain HFL of 126 meters. We compare the top structure's physical bed against the bottom structure's maximum water level. Because the 126-meter flood level clearly exceeds the 120-meter bed, we confirm this structure as a siphon aqueduct. In our second case, the top drain's bed level is 252.2 meters, and the bottom canal's FSL is 253 meters. Running the same mathematical test, the 253-meter FSL is greater than the 252.2-meter bed level. Therefore, the structure must be a canal siphon. By running this strict diagonal comparison across the survey elevations, engineers arrive at a consistent, mathematically determined structural choice for every site condition. There is a topographical anomaly where this vertical differential does not exist, when both the drain and canal bed levels are exactly equal. This specific four-way, same elevation intersection shown here is formally known as a level crossing. Level crossings are less than ideal because they necessitate the temporary mixing of natural drainage and the canal supply. For minor, low-volume streams, engineers use inlet and outlet structures instead. The stream flow is admitted directly into the canal bank and subsequently discharged through a leading channel further downstream. These coplanar designs are exceptions to the rules of flow separation, utilized only when vertical elevation differences vanish. Routing water through these structures solves the geometric problem, but it introduces a secondary threat to the infrastructure. Forcing large volumes of water through constricted siphons or over elevation drops imparts massive kinetic energy to the flow. These highly turbulent rapids create chaotic underwater currents that strike the structural boundaries with significant destructive force. This excess energy can lead to rapid structural cavitation and severe scouring of the downstream riverbed rock. Safe canal infrastructure requires immediate downstream mitigation to manage this kinetic energy before the flow damages the natural channel. This requirement is met through the installation of engineered energy dissipators immediately downstream of the crossing. A common solution is the stilling basin, using a deep pool to absorb hydraulic shock and prevent cavitation. Residual energy is neutralized by baffle dissipators. For tailwater depths greater than 1.1 times conjugate depth, engineers use slotted roller buckets. The cross-drainage problem requires strict dual-layered control. The designer must enforce precise elevation hierarchies to keep water sources isolated, while systematically managing the kinetic energy outputs that those structures create. By mastering the elevation matrix and energy dissipation, engineers convert irregular natural topographies into predictable and controlled hydraulic networks.